Where'd from computer go? All right, talk to me here. The inverse trig function. How we doing? Was that pretty cool? Was that like, eh?
Quite honestly, I did not understand it from the lot.
Okay.
Kind of big, but
Uh-huh.
that's just
Thank you for saying that. That's first of all, that's good. Second of all, should we go through the inverse trig function again, just sort of see if it just kind of bring it back to reality here
Maybe you
of
could
things.
do it with cosine instead of, or inverse cosine instead of inverse sine.
Mm,
Another
mhm.
example, just so you can see the other direction.
Okay, I do want to go through this whole process where we got it from, just real quick here, and then let's do. I'm going to quickly do sine, just so we have it. Okay, Kate, would that work?
Yeah.
So real quick here, where does this come from as well? It comes from the fact that we can do a derivative, and we start off by doing this derivative right here. So we say, okay, we're going to take a derivative. Oh, sorry, real quick here. Where's the proof to it here? Yeah, that's the proof. Sorry. We do the chain rule inside here. That's what happens first. So this is totally abstract, right? There's no sine function. There's not x squared, right? We just think of the fact that the chain rule says, I take the derivative of the outside function. I keep the inside function exactly the same, right? And I take the derivative of the inside function. That's what it does. So in this case, this is just function inside another function. Very generic, right? Very abstract. But we're going to take the derivative of the first function, keep the inside function exactly the same. Then we take the derivative of the inside function. On the other side, the derivative of x is just 1. So we have this relationship that just falls into place. If we divide through by this piece, we get a derivative of the inverse function, which is just a relationship of this right here. It's the reciprocal of the derivative of the outside function. That's what it is. Like, weird. That's so cool. And so then we start using it. So we say, find that we verified it here. We can go both ways. You could either go, so we're going to try to figure out the derivative. We want to take the derivative of this guy. So we say, okay, that's fine. I could do it directly. I could do it directly by doing the quotient rule. That's what that is all done there. But just for fun, let me see if I could just do it by taking this whole concept of this little function right here. I'm going to do it by this formula. I'm going to take the derivative of the inverse function by doing the reciprocal of the outside function times that. All right, so we do that. We find the reciprocal. I'm sorry, we find the inverse function, which is right here. Here's your inverse function. So then we're going to follow our formula now. We are going to take the derivative of the outside function. We're going to stick the initial function inside that one, and then we're going to take the reciprocal, and we find out that that's the same answer as that right there. So this little rule is king right over here. That's what we want to do. We want to stick to it. So in order to take the derivative of an inverse function, we actually take the derivative of the outside function first. Stick the inverse function itself in it, and then just take the reciprocal. 3-step process. Boom, boom, boom. Okay, then we say, okay, that's fine. The question is, if I could do it by the quotient rule, why am I doing this other rule too? That sounds stupid. And so it does sound stupid until we get to the whole concept of two things that flow out of it. First of all is we're going to make rules that have not existed before. We have no rules for fractions in the exponent. Initially, a long time ago, in the same classroom, we had rules only for integers. But those two are actually inverses of each other. It's perfect. So hold on. If I take a cube root, the inverse of it is x cubed. I can take the derivative. I can follow this formula again. And the formula turns out to be the same exact formula for power rule formula, right? You just stick the exponent in front, subtract 1 from the exponent. But what we've done is we've created a new formula that did not exist before. Now we can take fractions inside the exponent, do them the same way. So what emerges is two extra properties right here. Emerges that we can actually take the power rule and extend it into the rational function, the rational numbers. We're good? That's one thing. Second thing is, boom, wonderfully, we get to take derivative inverse trig functions. We developed them in trigonometry. That was last year. But we were not able to take derivatives of them. We could take derivative of sine. So what we do is we do the exact same thing. We're going to use that little rule. We're going to take the inverse of the inverse function, which is just the original function. We're going to take the derivative of this guy, which will be cosine, and we'll stick this guy back in. We're good there? And then we're going to take the reciprocal, that three-step process, right? Take derivative of the outside function, stick the inverse back in, take the reciprocal. So let's do sine real quickly here. Inverse sine again. Let me see, make sure I'm recording. Yep, okay. So I'm going to do inverse sine again, just real quickly here, just to get us going here. So I want to take the derivative of the inverse sine function. Can't do that, no way, impossible. So I said, okay, maybe I can. The derivative of the inverse function is that little formula again. So that's the derivative right there, right? That will mean derivative. That's the inverse function. And I follow this little formula. So then all I got to do is, instead of doing that one, I'm going to figure out the inverse of the inverse function. So I'm going to get this little function. Okay, good there. You guys talk to me. Are we good there? I'm just going to putting things together. Hopefully just fall in place. So instead of taking the derivative of the inverse function, I'm going to take the derivative of the original function, boom, which is just cosine. Awesome, got that done. So I'm going to follow this pattern. So what I just did is I just did this little piece right here. Next, I'm going to take the cosine function. I'm going to stick the inverse function back in. I just did that piece right there. And then I just need to take the reciprocal afterwards. Okay, this is where it gets a little bit fun. We can put all one under one. I just kind of did it in pieces here, just so it doesn't go crazy here. Okay. Talk to me through this here. So if I understand this correctly, this is sine inverse of x, right? And x could be just like x over 1. So let's go over here. Let's draw our triangle. And let's go back to our trigonometric definitions here. Cosine is adjacent over hypotenuse. Is that right? Sine is opposite over hypotenuse. Are we good there?
Yeah.
Boom. Okay, so that means hypotenuse is 1. The opposite sign is x from that definition. Good there so far?
Yeah.
What we want is we want adjacent over hypotenuse. So based upon this right here, can we get our third side of a triangle? Absolutely. Yeah, if we want to just, I'm going to just put n, that okay, for n. I'm going to solve for n. So I know Pythagorean theorem says x squared plus, n squared plus x squared is equal to 1 squared. I'm going to solve for n. I'm going to subtract x squared from both sides. And I got myself this right here. I put a plus sign because it's an actual length, right? It's a length of a triangle, so I don't need to put a negative. So that little piece there is the square root of 1 minus x squared, which is technically the adjacent side for my cosine curve. So that means this guy becomes the adjacent over hypotenuse, which just becomes this. Good there so far. So that is the sine inverse inside the cosine function. That's cool. This is awesome. Sorry, let's get to my stuff here. Okay, so then the answer is just the reciprocal of that. So now we're going to include that little 1 piece there. So final answer, 1 over the square root of 1 minus x squared. Done. And the fun part, you guys ready for this? Go back up here to the top. The derivative of sine inverse is an algebraic formula. There is no trig functions inside here whatsoever. It's not sine going to cosine. It's
What's that say there? The cosine times sine inverse x. It says adjacent and opposite on top.
adjacent, hypotenuse.
I'm going both of those with hypotenuse.
Uh-huh.
Okay, thank you.
Sorry, opposite and the hypotenuse again. Chicken scratch. Sorry, please ask me about my chicken scratch. That is so cool. Okay, so
That's
the,
how it makes sense. We would be limiting the inverse sine to only be like that curve. And that's not really, it's not like the sine where it's repeating like that.
mhm.
So
Yeah.
the derivative wouldn't necessarily need to be another function that repeats like that also.
Mhm. So that's the sine inverse graph, right? It goes from -1 to 1, and it goes up to pi over 2, negative pi over 2. Okay, so yeah, so we just got a formula that gives us the instantaneous slope at any one point over here. We good? Okay, the funky thing is, what's the slope right at 1? Doesn't exist, is that right? Yeah, can't exist because then you plug in a 1 into here, so it actually goes up into infinity, really, right there. Okay, so let's go on here. Inverse cosine. Okay, let's do this one together, and then I'm gonna just give you guys the rest of it here. So let's see, there's 6 trig functions. I'll do 2, and then you guys get the rest real quickly. So I want to find the derivative of cosine inverse. Oh, so let me do this like a little bit, each of these stages here. So cosine of x. All right, if that's the case, let me kind of do it. Yeah, I'm going to do it in format here. So, okay, so I'm going to do is I'm going to say, okay, g of x is going to give me cosine inverse of x, which will then become the inverse function. The original function would be cosine of x. There it is. I've defined all my functions. Okay, good there. Defined all my functions there. Now I'm going to take the derivative of the original function. I think this one's negative sine, is that right? Negative sine, that's cool. Okay, the step 1 is done. Now I'm going to take the inverse sine. Once you do a couple of these, I think it makes sense, or at least the process is easy. Okay, so let's set up our little triangle now.
We know it's exactly the same. It's just that now the adjacent is x. And we want them to find the opposite.
Mm-hmm.
And the hypotenuse is still 1, so you can just.
It would still be 1
It's
minus
just
x
negative.
squared.
Perfect, so that's x, that's 1. And this little value right over here. This is going to be, I'm going to put n squared here. So just for completion, say x squared plus n squared is equal to 1 squared. Voila. And exactly what we had before, right? N is equal to the square root of 1 minus x squared. That goes right up there. Boom, is equal to the square root of 1 minus x squared. Done. Okay, so now let's see how this works out. adjacent over hypotenuse. Now this one becomes opposite side over hypotenuse. So I think we're going to go with negative 1 square root of 1 over x squared from there. Okay, you guys talk to me here, just make sure. Pick on the people that are quiet here. So, Kate, we're good? Taya, we're good? Okay, I just want to make sure that you guys know where each of the pieces are coming from, because you're going to do one yourself in just a second here. Taya, where do you have a question? Like, oh, where did this one come from? Or how did you get this? Or are we good?
I guess it's just not.
Okay, okay. You set up the triangle, you solve for what is left over, you know the hypotenuse is 1, and therefore you're going to choose the definitions of that. And I think
Wouldn't it be negative sine would be negative n over x times 1 minus x squared? They're the square root of 1 minus x squared.
Say again, Kate.
So wouldn't it be negative sine, which is negative n over x, is opposite over hypotenuse, times?
Oh, gotcha. So this right here, relationship is not a times relationship, not a multiplication. It's a one function inside another function. And so the way we get out of it is we know the definitions, and we're going to use this little guy to build our triangle. So the first thing that we know is that that's x. And this is x over 1, right? So that means we know our hypotenuse is 1. And then we have this little extra missing side right here. That's always going to be the case. We've got this extra missing side. We solve for it, and we get a square root, some kind of function of square root inside there. And we go from there. Okay, so finally 1 over the derivative of g of x is equal to negative 1. I'm going to just take the reciprocal. Whoa, that's not what I want. That was interesting. Okay, and I think we're done. Is that right? There it is, that little piece there. So off to the side here. So the derivative of cosine inverse of x is equal to negative 1 over the square root of 1 minus x squared. Done. Ooh. All right, how are we doing? Good so far, kind of making sense. Is the process okay now? So the fact that you start off with the inverse function, you go back to find the original function, then we take the derivative because we already know the derivatives of the regular functions. I think this is probably the step that's kind of the new stuff that we don't really explore that much right there. I'll help you with that if you need to. And then the reciprocal is just easy. So that's the whole fun step right there. Okay, here it is. You guys ready? So, Taya, you get tangent. Eli, you get cotangent. Kate, you get secant. And Sadie, you get cosecant.
So basically, you can pretend that whatever the inverse thing is, it's just theta. It is just theta. So that just kind of gets cut out.
Yeah, almost in the sense what you do is you go from inverse function, right, to a theta, and then from theta back to your trig function. All right, so here's what we need to know. I need to know at the end of it all, I just need to know the formula. Give me the formula that gives me that. Okay. Now you probably will need the original formulas for the trig functions, right? Just real quickly here. So I'll set that up. And let me look up those real quickly here. All right, so the derivatives of the trig functions here are given right there. So we've done sine, we've done cosine, we've done these two here. So we got, so derivative of tangent is secant squared. That's kind of fun. See what happens there. Cotangent is negative cosecant squared. So you got the little square thing happening again. And then for secant and cosecant, it turns out to two different functions here. So you're gonna have to plug in, you have to do it twice in a sense, each one of those. Okay, I'm gonna let you guys struggle with it. That's part of it. And raise your hand, let me come by, I will help you as you kind of go through the process. All right, so just real quick, I want to show you just all the formulas that are here. I want to hide the toolbar. No, that's not going to go. Okay, never mind. I'll just keep the toolbar. Okay. Oh, there it is. Are we good there? So there's the formulas, particularly for Christopher and Enrique. So you guys have those. Pause the video if you need to. I'll go from there. But we're going to go on to example number 5. Just real quick here, let's start using the stuff. So again, calculus is you build up. Once you grab the formula, you don't need to go back down to the definition. Could you imagine doing this? Going all the way back to the definition of derivative and then doing it? Nah.
That's the nice thing about calculus. Once you get there, it's way simpler.
Uh-huh.
And then when you do the like homework after you've already progressed past that point.
It's so tedious.
Yeah, but if you go like learn more stuff and then do the homework as older and then you're like, oh, I already know.
Yeah.
Mm-hmm. All right, so find the derivative of this guy and of course, there's something called the chain rule here that's happening, right? Because we still have the chain rule itself. So now that I know the derivative for sine inverse, I think I'm good to go. So off to the side here, just the derivative.
The chain rule plus for multiplication.
Multiplication, off of the back end. I think it's the square root of, it's 1 minus x squared, is that right? Just real quick, can you guys check me on that one?
Yeah, 1 minus x squared.
Perfect, okay, so that means the derivative of the sine inverse is going to be, let's see if this works, 1 over the square root of, it's gonna be 1 minus, but now it's not x anymore, it's actually 2x cubed. So
2x cubed squared.
Squared, and then the chain rule now comes up because it's no longer x.
2x cubed.
It is going to be, oh no, it's the derivative of 2x cubed.
So 6x squared.
6x squared is good.
Wait,
Are we good
you
there?
don't multiply. Oh, wait.
That's the answer.
You good? Hey, we got to clean it up a little bit here, but essentially that is the answer. So on top, we're going to be left with a 6x squared. On the bottom, we're going to be left with a square root of 1 minus, what is that? That's going to be a 4x to the 6th, right? Boom. Okay, and then talk to me. Are we good now?
Yes.
Okay, I got a b for you as well. Different function here. I'm going to go h of x. H of x is equal to tangent inverse of x squared. Hey, x squared would be fun. All right, I'm gonna go with it here. So let's see, the derivative of h would be 1 over 1 plus, so it's x squared in here, right? So this would be x squared squared minus 2x, or times by 2x. I think I'm good. 2x over 1 minus.
Why is it times two?
Because of the chain rule. So it's going to be the derivative of the x squared. Talk to me if that makes sense.
Yeah.
Cool. Okay, and then of course c would be kind of fun. M of x. M of x is x squared sine inverse of x. How about that? Okay, no chain rule, but I'm going to give you a product rule. On the homework, I'm sure there's going to be a product rule that's sitting with the chain rule.
Oh.
That'd be fun too.
Yeah.
Am I going to do it in class? No, I'll let you guys struggle with it.
You don't want to leave a sign next, or sign inverse x in our answer, do you? Or does that?
Oh yeah, you can leave it there. Yeah, absolutely. That's totally fine.
I don't like that either. It's just like, it seems very messy.
Oh no, now it's messy.
If I got the right answer.
No, I think I'm pretty sure you got close there. Okay, so this is a product rule, right? So it's gonna be the derivative of the first. So everybody okay with 2x? The second is just gonna be exactly how it is. There's no change there, plus. And it's going to be the derivative of the second.
1 minus, or, yeah.
But multiplying times the,
It's just messy.
uh-huh.
That's all,
And-
so you don't have to do anything else. I do that.
Let's see, maybe just put the x squared on top of that little root. That's about it. That's good enough. Okay, boom, awesome. Okay, we're good there. And then you guys will have fun taking derivatives of this stuff. And then example 6. And here's where we get fun. So we are going to launch a rocket. And we have a camera angle. Now we know pretty much the trajectory of the rocket. That's why you have those wonderful clean images of rockets when they go up in the air. The camera is positioned 2,000 feet from the launch site. And then we have a rocket that just goes up in the air, blasting like this. Okay, so I do want to know this one here. So find the formula that will give us the movement of the camera. So this camera is not just a camera. This camera, what it does is it's based upon a formula. I
So we
turn it
change
on.
that angle,
So that that rocket's gonna be right in the middle of our view the whole time. And so I'm gonna create a formula that does that. So once they say go, I turn on the camera and it just takes the video, and then find the instantaneous movement in radians of the camera when the rocket is, maybe a fun little number, 4,582 feet in the air. Boom and
Wait,
boom.
so do we actually want to do the second part first?
Well, I'm thinking what, you need to figure out the formula first. Once you know the formula, then you plug in the value.
Yeah. We're gonna find the slope first and then just do that.
Yeah. Now, the only issue that I have, so I should put this 2. 1, 2, 3, 5 to 5 decimal places. I should put that in there because you'll see that it's very slow movement. Initially, when the rocket takes off, right, yeah, you got to pan it really fast here, but after that, then it's just going to be a slower and slower movement here. Okay, let's talk about it. Let's see what we got here. So I need the camera angle itself. I need a theta movement here. So based upon that right there, you guys help me out? What do we got here? I'm not trying to find the distance from the camera to, I don't care about the distance, right? Because I'm going to have that. That's a more focal point problem at that point, right? I'm caring about the movement of the camera up and down. So I guess I need help. I need to figure out what theta is in the first place. What's the trigonometric relationship that I need to set up?
So are you trying to just find the angle position?
Yeah, so I got this guy here.
The angle when the rocket is at 4,182.
Not now. I don't care about the 4,582 yet. I just need to figure out the relationship between the going up in the air, right, and then that little movement. And the hint is I don't care.
Oh, so we would just.
I don't care about the hypotenuse at all because.
We could just do tangent, and then as x change, as the rocket goes higher than.
Good. Hold on. I like what you said. As x changes, okay, I got it. So this better be x over here, right? It could be h, whatever you want, but you guys have some kind of variable there. So then that means this is the relationship is.
X over 2,000.
Yeah. Yeah.
Sine inverse would be.
Got that right there, right? Boom. Perfect. So that means I have a relationship theta is equal to tangent inverse of x over 2,000. Okay, I think we're set. I think we're going somewhere here, guys. And Taya, here's your one example that you're talking about. Okay, you guys help me out here. I didn't know the derivative then. What's d theta? dx. Also notice it's not in terms of time either, right? Because it would have been dt. But this is just in terms of movements.
There's 1 over 1 plus x over 2,000 squared.
I think I'm gonna go for it. Yeah, d theta dx is 1 over 1 plus the original 1, like that. Is that what it is? Multiplied by 1 over 2,000. Is that right? Eli, is that what you had? 1 over 2,000? Okay, so cleaning it up, how about this? 1 over 2,000. Parentheses 1 plus, 1 plus, what is that, x squared? Whoa. That's a big number. I'm going to write it like this. That okay? I'm going to write 2,000 just squared still. Good there. Cleaning it up a little bit more. I think I clean up. Can I distribute the 2,000? If I distribute the 2,000, it looks like this. This is probably the cleanest version. It's going to be. There it is.
You think the derivative would be inside.
Oh.
I think that's it right there. Boom. I can make it into, yeah, but then it gets big again. So I think I'm gonna leave it just like that. That's, don't like that anymore.
But the derivative of 2,000 isn't anything.
It's the derivative of x over 2,000. So the derivative of x is 1, and then we're just left with,
But don't we just take
There's a
2,000
derivative
out?
of the 2000 too.
talk to me. If I have x over 5, right? The derivative of x over 5 is 1/5, right? Because you take that as the derivative, as a multiplier
Yeah,
in
I
a sense,
see
right?
it happens.
Then that goes away. You're thinking about probably the chain quotient rule, but then you get a 0 in there, but yeah, you're still gonna have that in there. No? Okay. Nope, never mind. The laser pointer. Yeah. Okay. That's cool. I got that. I like this. Now the question is, can we simplify it some more, I guess? Because we don't really like complex fractions. We're not considering that simplified if we have complex fractions. So let's do this here. I'm going to multiply both sides by 2,000 on the bottom and 2,000 on top. And I'm running out of room. So let's see what happens here. This is going to be final answer. How about 2,000 on top? As I distribute this little guy, that's going to give me 2,000 squared plus x squared. You can write it like that. Sorry, we're doing a lot of just simplifying here.
That's gonna be a small.
Uh-huh. So that's my final answer. Are we good? It's 2,000 over x squared plus 2,000 squared. All right. Got that one. Now we just need to figure out. So that's the end of part A. Part B, I should just label as part B, is going to be plugged in value of 4,582, which we'll probably need to have to use a calculator here. We want to use the notation for it, the way the book does it. It does this, which is kind of nice notation. It's very clean right here. So we have d theta dx. And if you guys can do that in a calculator here, this is a calculator exercise now. And so, man, sure don't want to do it by hand. I want to punch in this whole thing into a calculator at that point. And so careful, make sure you have put extra parentheses on the bottom
5 decimal places.
and 5 decimal places. All right, what is the movement of that camera? It should be just a single digit. Should be just like 0.00000 something. So what'd you guys get? Not that.
8.00169 e to the negative fifth.
Oh yeah, okay, yeah.
So you
That's
just put, you just move the decimal
Oh,
place
you
one by
remember
one.
that, yeah.
Yeah.
And it's 0.00008. So.
another O or no?
No 4 zeros and then the 8, yeah.
Okay. So on your calculator, you guys know that, right? If you have e to the negative something, that is the decimal points backwards. Right. Cool. There it is. There's my, again, this angle is moving very slowly. It's a radian measurement, hardly moving at that point. Right. In the beginning of it all, yes, it was moving kind of
I
fast,
mean,
right?
that's the slope. That's the instantaneous slope.
Yes,
Not the
it's
theta.
correct. Yeah, that's how fast the camera angle is moving
In what measure?
in a circular direction, right? In radian measurement, so it's going from here to here. Okay, boom, almost time. So let me just give you just a quick. So that was 3-7. We good? 3-7. We've done inverse trig functions and inverse functions in
Do you
general.
have class on Fridays?
See again?
Do you have class on Fridays?
I know.
All the time.
if we make a schedule that way here. So real quickly, let's do this.
I think we all have free period or like period after. Don't we all have that? Yeah, yes, we do. Do a class.
He doesn't want to admit that he has a free period because then he might have to come in.
My free period is busy. That's when I go to the gym, that's my dedication.
You have a ton of free periods and not thinking of elective. You have plenty of time.
So I go to the gym during free periods, and I leave during my life.
All right, let's go with it. Implicit differentiation. Here's the next big piece I want to show you guys. So we did this before already. And this is, I'll do a whole video thingamajiggy on it here, but just a quick intro. In fact, I'll intro 3.9 as well, just real quick here. 3.8, just so we know. Ready? Let's take a circle, for example, here. So x squared plus y squared is equal to 25. That'll probably be a good way to do it. Notice this one, we can't get f of x out of it, right? It's the conic section pieces from algebra 2. And so we have this relationship between x and y and a constant. And so in calculus, the question is, well, what do I do? How do I do this here? And so this little, from the last problem we did, you know, how we do d theta over dx, right? That little piece there, we can still take a derivative. And here's kind of, let me give you the big pieces and then we'll stop here. So if I take a derivative of both sides, I can do it at the same time. So what happens here is I'm going to take the derivative of, let's see, I'm going to do this here. The derivative of x, the derivative of x squared in regards to x. I'm going to take the derivative of y squared in regards to x, and then I'm going to take the derivative of 25 with respect to x. We're good?
Why is it respect to x again?
I could do it with respect to y as well. It doesn't matter.
Why
It's
do
just
you
going
have
to
to
be one.
with respect to anything?
Yeah, because you're always going to do it in terms of one single variable in the process. It has to always be in terms of a variable.
That means your answer for the derivative of y squared is going to be in terms of x.
Mm-hmm.
Oh, because you have, okay.
You have to get to one variable so you can solve.
Uh-huh. So the way we say it's slope is because it's the change of the y value, right, over the change of the x value. That's why it's slope.
Yeah.
So what happens here is you get a 2x out of this. And notice what happens. It's going to be a dx. I took a derivative of x with respect to x. This one, it's going to be 2y. I took a derivative of y with respect to x. And this one's just going to be 0. I don't care. It's actually dx over dx. So notice what happens is these two just cancel off, right? Because they're an identity. So you have yourself 2x, 2y dy dx, and you got yourself a 0. That's called implicit differentiation. We did not need to.
Why did you keep the dy over dx? Didn't you already take the derivative of it? So why did you keep the notation in?
Sure, because I took a derivative of y, right? It changed from y squared to a 2y, right?
Yeah.
So I've changed the y variable into its slope form, right? So I have to account for that. Now, initially when we used to do them, we used to go like this right here, right? 2x minus 3. So it was, oh, that's just dy dx is equal to 2. Right, so it's really just the notation saying, hey, the notation, how about if I just do it on this side?
Keep it
Let's see
in
what
there.
happens. And so it does keep just perfectly here. And we subtract the 2x from both sides. Negative. And then, lo and behold, we get ourselves this, and this turns out to be the formula for all the slopes all around the unit circle. Just put me an x and y coordinate into it that's on the unit circle, and that gets me the slope for it. All right, on past time. 1.9, I just want to give you a brief intro to this one. It's going to be just like we did the trig functions, right? It's going to be the derivatives of, hey, what do you know? The exponential functions and the logarithmic functions. That's the end. And at that point, we finish with our
Logs.
oh shit. So at that point, we'll be done with all this theoretical stuff with derivatives. Then we move on to application. So let's stop here for today.
Can you go back one slide for a second?
Sure.